Hi, welcome back to es346 Basic Thermodynamics. This is module 5.1 on mass flow. The sections in the textbook are Sengel and Bowles 5.1 to 5.2. Let's quickly review the course outline as we move into Chapter 5. So what we'll be doing in this module is Chapter 5, and what we're discussing are open systems, and we'll be looking at both steady and unsteady systems in there. That'll go ahead and wrap up the first law of thermodynamics. Here are the three learning objectives for this module. At the end of the module, you will understand the conservation of mass principle. You'll be able to relate volume flow rate and average velocity, and you'll be able to quantify the energy associated with mass flow. So let's discuss velocity and volume flow rates. So what this diagram shows is a cross-section of, for example, a pipe. And we have fluid moving from the left to the right. And because of friction, you're going to have zero velocity right at the wall of your pipe. And then as you move in toward the center of the pipe, the velocity increases. And you can see this with the direction, the magnitude of the arrows. And you can kind of think of if you were to be squirting honey out, or you can see a very viscous fluid, this idea of this velocity profile that moves through here. And what this means is that the velocity at any particular point depends on where I am in the cross-section of this pipe. The same argument would apply for square ducts as well. So if we wanted to talk about an average velocity, we could define the average velocity as, well, what we'll do is we're going to integrate over the area. So here's my double integral over the area of the velocity, the local velocity. So this local velocity that I'm integrating is each one of these arrows. And I'm integrating it over a differential part of the area in there. And then if I go ahead and divide back by the area, I'm going to end up with an average velocity. And so on this diagram, we see we're going to end up with a number that's independent of the area. It's got one magnitude. And yeah, there's going to be one velocity at one point in the pipe that also happens to be the average velocity. But the nice thing about this average velocity is that since it doesn't depend on the pipe, I can then go ahead and define a mass flow rate, m dot, as equal to this average velocity times the cross-sectional area of the pipe. That's going to give me a volume flow rate, so then I'm going to go ahead and multiply by the density of the fluid. And none of these depend on the particular location in the pipe. This is often called a cup mixing approximation. And the reason this is used is you can imagine if I was to take, for example, a measuring cup, and I have a pipe that's filling it up with some fluid coming in, and I wanted to know what the average velocity was, I could just go ahead and fill up my cup. I would have some particular volume. I would multiply by the density, and I'd have the mass flow rate, which I could go and then correlate with an average velocity. All right, let's do a couple examples of this concept of the average velocity and using a mass balance. And so here what we have is a pipe where fluid is coming in at 2 feet per second, and the area here is 1 square inch. It should be 1 inch squared, and this should be 4 inches squared. Those are areas, cross-sectional area. The pipe expands into a larger area, and what we want to know is what's the average liquid outlet velocity. So we have a liquid, which means that we have something that is incompressible. And we'll see that that's going to make the solution of this problem a little bit easier. So what we're going to do is we're going to apply a mass balance across here, which says that we know that the mass flow rate that goes in to my boundary equals the mass flow rate that comes out. And what we just saw is we can go ahead and relate this to average velocities, where I've got V, average velocity, times the cross-sectional area at 1, times the density at 1. That's going to be equal to the velocity at point 2, cross-sectional area at 2, times the density at point 2. Now, if this is a incompressible material, we have a constant density, I can go ahead and cancel out those two terms. And I can now go ahead and solve for what my outlet velocity V2 is. I'm going to have V1, and then the ratio of A1 over A2 is going to be equal to my average velocity V2. So I can go ahead and plug in those numbers. V1 is 2 feet per second. And then the ratio of my areas is 1 over 4, for square inches. And so then that comes out to be 0.5 feet per second. And so that's the average outlet velocity out here. All right, let's go ahead and look at a similar problem. But now what we're going to be doing is we're going to be dealing with air, which is a compressible material, which means its density is not constant. So once again, I have an inlet area of 1 square inch and an outlet area of 4 square inches. And so I'm going to again apply my mass balance, which says that the mass flow rate going in is the mass flow rate that's going out, and then express that in terms of average velocities. So I'm going to have V1 times A rho 1 equals V2 A2 rho 2. Now, in this case, I can't cancel the densities because I can see with this change in pressure as I move through the pipe, I'm going to have a different density. I need to determine what those densities are, and I can use the ideal gas law that says PV equals mRT, and I can rearrange this in terms of density because I can then see that P over RT is M over V, and that right there is density. So for each place that I have density, I can replace it with P over RT. So let's do that. V1, A1, and for rho 1, I've got P1 over RT. Now V2, A2, and then again for the density, I'm going to go ahead and replace this with P2 over RT. And the problem says this is a constant temperature, so I can go ahead and cancel out my RT terms, and now I can go ahead and again rearrange this to go ahead and solve for what V2 is in terms of V1 and the ratios here. So I've got V1, A1 over A2, P1 over P2. And we can go ahead and put some numbers in there. So the initial velocity was 2 feet per second. The ratio of my areas is 1 over 4. And now I've got my pressures where I have 30 and 20. But we want to be careful here because this over here is an absolute pressure. This was given in a gauge pressure. So P1 is going to be 30 plus 14.7 over 20 plus 14.7. So these absolute pressures, because I'm using the ideal gas law to get my density relation. And that right there is equal to V2. And that velocity is about 0.644 feet per second. All right, I want to discuss this concept of flow work, and we'll just do kind of a theoretical discussion of this first. And so what this diagram shows here from the textbook is I have this volume, that's what CV is, it's a control volume, so the dashed line is an imaginary boundary. And what I'm going to do is I'm going to push some material into this control volume. So this is being showed with this piston. And this other piston will go ahead and hold that constant for now, so no material leaves. So we're putting in a little chunk of material that has a volume V, a pressure P, and a mass M. And so we're going to go ahead and push that into my control volume. So if we do an energy balance over our control volume, the change in energy is going to be the energy that I put in minus the energy that goes out of my system. Now here I'm just pushing material in. We're not going to have any other boundary work going on because my control volume is staying constant. There's no boundary work there. So WB is equal to 0 because the control volume is not changing. And we'll also assume that it's insulated for now, so there's no heat transfer going on. So that whole term right there is going to be 0. So the energy that's going into my system is going to be, well, there's energy associated with this material. It's got molecules, they're flying around, they have kinetic energy. And so they're going to have an internal energy. So it's going to be that mass times their internal energy. This is the mass of the material I'm putting in. Now, I've also got to apply a force to push this material into this control volume. And so we know we're doing boundary work at that point. So I've also got to include the boundary work. If I put some work in to put it in, that energy has to go somewhere. It goes into the control volume. So let's go ahead and look at solving for that boundary work. So we're just going to write down my mu term again. And we know that boundary work is always the integral of P dV. Now, if this amount of material I'm putting in is pretty small, so let's imagine that this is a really, really small amount of material relative to the control volume, the pressure really doesn't change much. So I can go ahead and pull that pressure out and say that M times U plus P times the integral of dV. And you realize that's pretty simple now. I'll just get mu plus P times V. And that's the volume that I went ahead of this small amount of material that I have. Let's express that in terms of intensive variables. So I have mu plus pressure, and I'm going to write this down as M times little v. because m times little v is the big extensive volume of that small amount of material that I'm putting in. And let's factor out the m's. So I have m u plus pv. Now we'll recognize this u plus pv term because that is h. So this is m times h. So what I've just shown is that the change in energy of my system, when I push a little bit of material in, is equal to the mass that I put in times the enthalpy of that material. And this is going to be a really important concept with open systems. Anytime material crosses the boundary, goes across that dashed line, the energy associated with it is h. It's the internal energy plus the product of its pressure times volume. All right, so let's go ahead and do an example problem here. And I have a steady state water boiler. Let me spell that. There's a T there. A steady state water boiler. And it's operating at 250 kilopascals, and it's delivering steam at 0.2 kilograms per minute. And we want to know what the heating rate is in kilowatts. So here's my system. I have a Q going in. That's what I'm trying to find. This is a rate term in terms of kilowatts. And what I have is it's a steady state boiler. So it's bringing liquid water in and boiling and putting vapor out. So a vapor there, liquid coming in, and it's operating at 250 kilopascals. So if I go and write my steady state energy balance, well, the rate that energy goes in is the rate that energy goes out. And if I look at the arrows going into my system, right, I've got my mass flow rate coming in times the enthalpy coming in, plus this Q term, Q dot, and that's going to be equal to the mass flow rate that's leaving out times the enthalpy that's going out. Now, again, I'm using H here because this material is crossing the boundary. It crosses it to get in, and then it crosses it to go ahead and get out. And if I go ahead and assume that this is coming in as a saturated liquid, it's not a bad assumption, and this is coming out as a saturated vapor, I know that this over here is x equals 0, and this is x equals 1 at the outlet. I can go ahead and rearrange this to say that Q dot is equal to, factor out the m dot, h going out minus h going in, which is m dot h sub g minus h sub f at 250 kilopascals, and that's m dot hfg. So if I go ahead and pull some numbers off the table here, my mass flow rate was 0.2 kilograms per minute. Let's get this in per seconds because they want the question asked for it in terms of kilowatts. So 1 minute is 60 seconds, and then my value of hfg at 250 kPa I pull off the table. That is 2181.2 kilojoules, and if I do that arithmetic, this comes out to about 7.27 kilowatts. So that right there is the rating of this steady state boiler.